The images shown have been created using only 8 LEDs. I've used the slow shutter speed on my camera whilst moving the LEDs from side to side. This creates a persistence of vision and makes it appear like there are lots of LEDs creating the image. This is sometimes known as light painting. This is created by turning the LEDs on and off very quickly, which is achieved using an ATMega328P, which is the same microcontroller as used in the Arduino. In this video, I'm going to explain the circuit, how it works, and how this has progressed from a breadboard design to a soldered circuit on a prototyping stripboard. In future videos, I'll be showing how you can create your own printed circuit board for the ATMega328P. So if you haven't already subscribed, please do so now so that you can find out about those videos when I've created them. A quick word of warning before I start. You'll see in the video that I'm using a kit for the components, and in the description I'll be linking to the source code which is from the kit supplier. However, please do not try and order the kit as it is no longer available. The website is up and I tried to order some more components from them. The website accepted my order and took my money, but they did not ship anything to me. They didn't respond to any of my attempts to contact them. Fortunately, I was able to get a refund through the PayPal buyer protection, but that was obviously a bit of pain, so please avoid that website. I will provide a link to my webpage in the description, which will provide details of the parts you need and about how to get an ATMega328P with a bootloader. I'm going to start the explanation by looking at the finished circuit, and specifically the 8 LEDs which are in a row. This is the important part. These LEDs can be turned on and off really quickly. This is used to create an image, and as you move the board from side to side, the light is captured on the camera and creates the image. Getting the timing right is important, but really this was just a case of trial and error, and it just took me some time before I was able to get the image that I wanted. We can now look at the circuit, which is actually quite simple. I've created this diagram in KiCad rather than Fritzing, which you may have seen me use on my earlier videos. So at first look, this may look a bit more complicated, but bear with me. I'm planning to use KiCad more and plan to add some tutorials on that in the future. That will allow me to create some more complex circuits, but I'll still be creating some content for beginners as well. Looking at the diagram, first you can see on the left the power supply. This is shown using power connector labels, which are used to save having lots of wires around. It's a technique I've used in Fritzing as well. Essentially, every time you see the +5 volt arrow, they're all connected, and every time you see the ground symbol, then they are all connected. I'm actually using a battery pack with 3 AA batteries, so depending on the battery voltage, it's going to be around 4.5 volts, but anything between about 3.5 and 5 volts should work. The capacitor is there to smooth the power supply, particularly as different LEDs are turned on and off. This is a small ceramic capacitor, so will respond quickly, but only have a small effect if, say, you quickly went from all lights on to all lights off and vice versa. In that case, you may want to look at additional capacitors, such as a 4.7 microfarad, but this works okay here. The large yellow block in the centre is the ATMega328P integrated circuit. And then there's a crystal across pins 9 and 10 for the clock. The connector at the top is used to connect to an UART, which is used for sending the code from the PC. The resistor and capacitor is connected between the reset and data ready pin of the UART, which is to trigger a reset of the pin when we want to send updated code. Then it's just 8 LEDs connected to the corresponding pins. I would normally use a resistor for each of these LEDs to protect the LED and the chip from a too high current, but this just relies on the LEDs being turned on and off very quickly. Note there are 2 power supplies on this circuit, one for the UART and one from a battery. You should only ever connect one of these at a time, so disconnect the batteries whilst uploading new code, and then remove the connections to the UART when ready to test. The kit provides this as a breadboard layout, which I've shown here. I've squeezed this onto a 1/4 plus size breadboard, which is smaller than you normally get, but you'll see why this is important later. First create your circuit on the breadboard, and then you transfer it onto a stripboard or sometimes known as a Breadboard, or there's various different ones. I'm going to just show you the one that comes with this, which is your traditional, or quite close to your traditional, in that all the copper strips just run horizontally. And you can also buy these direct. You can buy these as big sheets, and you can build your own circuit on these. So one of the challenges of these, though, is you might need to cut it to size depending upon your circuit, but also when you want a integrated circuit to be mounted on these, such as the ATMega microcontroller, then you have to break the tracks so that there's not a short from one side to the other. You can do that using a tool such as this. This is a proper stripboard cutting tool. It's like a sort of drill end on it, and with a screwdriver type handle. Or you could use a Stanley knife or a drill by hand if you wanted. Another way is you can get various different boards. This particular one is designed for integrated circuits. It's got power lines that run inside the integrated circuit, so in between the tracks, and then you've just got 2 pins either side. Or for when you're building these on breadboards first, these are really good in that these are basically the same layout as a breadboard, and this is for the half-size breadboard. You've got the power rails, and then you've got these that are connected, and that allows you to basically take your circuit exactly as it was on the breadboard and straighten and solder it up, which is really convenient if you've just designed it like that and you wanted to make a more permanent thing. So I really like this, and in fact I've got one that's a quarter size, so half of the half-size breadboard one, and this circuit should just about fit on that. So this is the one I'm planning to use for this. So I'm going to have to just squeeze some of the components in a little bit more, because this has only got 15, whereas the example on the circuit has got 18. I'm not going to build it on breadboard first. I'm just going to put it straight onto this using that layout to show you how you can make a permanent version. Header connections, so this one's at a 90 degree, so it allows you to mount the headers for connecting to the UART at 90 degrees to make it easier to connect to. And this, which is an integrated circuit holder, and the idea of this is 2 things. One, it means you don't have to solder directly to the processor. You can solder on here, and then you can remove the processor, whether that's because you want to re-image the bootloader, or you want to take your processor. You can potentially have 2 kits, and they can take the turns in having the processors, as long as you, or the microcontroller, as long as you reflash them each time. But just, I think it's probably good practice just to use these when you're making circuits. One thing you do have to be careful of if you buy the ATMega328 is to make sure that it has the bootloader installed. So what this is when it comes out of the factory, there's no code on the ATMega328 Pro microcontroller, and so it wouldn't do anything. The bootloader has to be programmed onto it, and then once that's on, when you connect it to a PC, it will look for that and allow it to download the code straight away. If there's no PC connected, then it knows just to start running the code. Now you can buy them with and without the bootloader installed. If you go for a traditional electronic component retailer, then you'll probably find that it doesn't have the bootloader. Whereas if you buy it from a maker site a hobbyist site, then it's more likely it does have one. Bought this one a while ago. I don't remember where I bought this from, but I've intentionally bought one of each. So this one's got a bootloader installed, this one's got no bootloader. The idea is that in future I plan to do a project where I build my own bootloader using an Arduino. So using an Arduino to program an Arduino. So that's something for future, but for now, if you buy this, make sure you get one with a bootloader. And usually they'll say if they've got a bootloader. If they don't say anything, then be careful, as they might not. Got the 16 megahertz crystal that I'm going to need. They were bought together, and then the other components are just standard ones from my my stock of bits and pieces I've got. The two 100 nanofarad capacitors and a 10 kilo ohm resistor used for the pull-up resistor. So with that, I'm going to get on and have a look at laying it out and start building it as a permanent circuit onto this little board. I've just got some tools ready that I'm going to need. Obviously the first thing is a soldering iron. So this one, it's just got a standard chisel tip on, nothing too small, nothing too bulky, and a stand to keep that safe. This one has got a digital soldering station with a digital temperature readout. Don't need anything quite this fancy, but this is quite nice. I like this. It's I set it at 350 degrees Celsius, which is at the higher end. Some people prefer to solder at a lower temperature, but I like to have a nice hot iron and then get the solder done as quick as I can, rather than having a cool iron. Need somewhere to wipe your tip to keep it clean. Quite often get a sponge which you just wet, and you can use that. But I actually like this, which is a brass wool type material, which you can use to clean the tip. Some solder, obviously, and this one's a lead-free silver solder. And when I'm soldering, I quite often use an extractor fan. I've got one here with a basic filter on. Just bring it in. The one downside of this is it's very noisy, so when I'm filming, I'll try not to use it too much, or I'll obviously I might have to turn the volume down for that. And some wire cutters. These are side cutters, useful for cutting the leads off the components once they're on. And I've also got some bits of Lego, and I'll show these possibly in use later. I just find they can be quite useful as something to prop the board up on when I'm soldering. You can get some more professional things like helping hands or something like that, but I just find a couple of bits of Lego are useful. Or you could always just use whatever else you've got around, just something that's going to prop it up. I'm going to start with the sort of smallest, low profilest components, the parts that are closest to the board. You position them on the top and then solder from the bottom, and the smaller ones make it easier for it to be while it's on against the table, and then as you put the bigger components on, it gets a bit further out. The first thing I'm going to put on is this resistor. Leaving space for the board to mount will be pin 8. Always double check when you're putting components on, because once they're soldered on, it's not impossible to remove them, but it is very difficult. I'm also just going to check and make sure that this is still going to fit. Yeah, it's not going to get in their way. I'm just going to break this to the right size first as well. 9. and then that will fit. So some people might bend the legs down, but I find if you want to get a nice neat solder, just leave them facing up, but what you need is something that's going to just push on that. So this is where the bits of Lego come in handy. So if I just balance that, as long as this is being pushed up from the bottom, then it should be okay. So just do first solder. So I'm touching the soldering iron to both the component and to the copper pad. You're going to heat them both up and then melt the solder into them. Hold it on for a second till the solder melts, remove the solder and then remove the soldering iron. And that's quite a nice solder there. Same for the next one. Move these components out of the way. So there we go, the first component soldered in place. I'm just going to snip off the leads, hold on to them when you do, so they don't go flying off and hit you in the eye or anything. And those can go straight in the bin. And then move on to the next component, which I think I'm going to use the probably these, the headers are probably going to be the next size. So position those where I want them. So it's when you get to bits like this that it's important that you use something to steady it and to keep it roughly about the same height so you get an even amount of wire sticking through them. I'll just put the first one on, and then it gives me an opportunity to make sure. So this isn't gone flush, but as I've only done one, I could potentially reposition that by hand. As if I'd left it until I'd done them all, then that might have been too late. So that's that row of connectors put in place. Now I'm going to put on the mount for the microcontroller chip. So there's a notch this side to indicate pin 1, so that's at the left hand side. With that. So that's going to sort of balance there. I'm going to put in diagonally opposite ones, check that it's soldered in correctly, and then go on to do the rest. And this gives me the opportunity that if the component is not flush, then I can reposition it. That one is really nice and flush, so I can just carry on and I'll solder the rest of those on. So that's the IC socket mounted on. And now I can put the capacitors in. I'll just do these one at a time. Again, chop off the leads. And now the next component will be the crystal. So the crystal is one part that I don't actually want to be completely flush, because these are copper tracks and the can of the crystal is metal, so it could cause a short if they were actually touching. So if I position it, I just try and position it so that it is slightly above the board. I'm going to move on to putting the LEDs on next. We've still got some wires to put on, but I'm going to put them in last because I need to sort of run them around the other components. Now, there should be two ways of telling an LED which is his anode, which is the positive side, and which is the cathode, which is the negative side. When you buy them, then if they're new, then almost certainly the longer wire, you see there's one's longer than the other, the longer wire is the anode to the positive side, and the shorter wire is the cathode, which is the negative side. The other way you can normally tell is looking for a flat part of the LED, because while it looks cylindrical from here, you're not going to be able to see this on the camera, but there is a tiny little indentation or a flat part on the side of the LED. Normally that is on the cathode, but in this case it's not, it's actually on the anode, and I've had this with some other LEDs I've bought, so you do have to be careful. The best way is actually to test it, and I actually did that. For soldering the LEDs, all the cathodes, the negative sides, go to a single row, which is marked with a blue line on my particular board, and then the anodes go to their respective pins on the microcontroller. Finally, there's some wires used to connect the power supplies from one side of the board to the other, and then the battery pack needs to be soldered onto the board as well. Now that the hardware is complete, it's just a case of downloading the software and flashing that onto the controller. You can download the software from GitHub. I'll provide a link in the description. This is the shrimping it./projects. And note that they no longer provide the kits, as I mentioned earlier, so don't try and buy anything from them, but you can still download the code, either clone it using one of these links or download a zip file and then install that, install the libraries into the IDE. This is the Arduino IDE. You do need a later version, and this version is 1.8.13, so this or later would certainly work. The one that's provided as standard on the Raspberry Pi repositories does not work, so you might need to upgrade that. Again, I've covered that in an earlier video. Once installed, then the files, there's several different persistence of vision, POV files that you can use. There's fixed patterns and there's the text and things like that. So the two I've used is the smiley for the smiley face and paint text, which I've used. It has the codes for all the different text letters and you just create a string. This is still set at the default, which is $. So you can just change that and then upload that using a UART onto the microcontroller, and then it should be ready to go. And this is the finished circuit all mounted on the battery pack. So I've soldered the battery pack to the power supply leads, and I've mounted it just using a elastic band around the battery pack and the circuit board just to hold it in place. You could use adhesive pads or something like that as well, but I think that does the job. It's easy enough to take off, change the batteries and use it. So now time to try it out. I've already flashed the image to it, uploaded the image using the IDE, and it's basically a case of waving this, switching it on, the lights come on, LEDs come on, flashing the sequence, wave this in front of the camera on a slow setting, I think about 1/6 of a second, and look for an image. So give that a go. Here you can see some of the photos that I've taken by using the slow shutter speed on my camera. This finishes the series of videos I've created based around these kits. In future videos I'll be covering more about the Arduino, as well as designing my own custom PCBs for the ATMega328P. So if you haven't already, please subscribe to see when they are available. Please like and share this video if you think others will find it useful, and I look forward to seeing you on a future video.